So now we're going to look at rewriting time-dependent perturbation theory in a form that's compatible with our annihilation and creation operators for these various different kinds of particles. We will have, as before, an unperturbed Hamiltonian, H0, such as the one we've been looking at for non-interacting fermions and bosons. And so that could be like this one here. Here's our fermion part, here's our boson part, presuming to start with in the unperturbed Hamiltonian that we are neglecting the interactions. Then we'll consider the interactions between particles, such as the electric dipole interaction we've discussed before for electrons and photons, and we'll introduce that as a perturbation. So here could be our perturbing Hamiltonian, which we've been discussing above.
Note, incidentally, that this approach works for any kind of particles. We could, for example, apply it to electron-electron scattering. It's not necessary that the interaction is between different kinds of particles. For the sake of definiteness here, we'll discuss a system in which there is one kind of fermion, which we can think of as electrons of a given spin, and one kind of boson, which we can think of as photons. This general approach is, however, appropriate for any different kinds of particles. To get started here, we'll briefly review first-order time-dependent perturbation theory, but we'll show it in the current notation. First, note now that the quantum mechanical states are those of the entire system. Previously, we might have considered only the electron state, treating the perturbation, such as an electric dipole perturbation, as being from something external to the quantum mechanical system, such as a classical field. Now the field itself is part of the state of the entire system.
So now our basis states must describe both the occupation of each single particle electron state and the occupation of each boson mode. Hence, we're going to write our basis states in the form used in the previous example. So this kind of form here, where we have lists of occupations of fermions among fermion single particle states and bosons among boson modes, as in our example that we looked at before. Specifically then, the mth state of this entire non-interacting fermion-boson system, or the mth state of an interacting system, as a basis state, can be written in the form we've been looking at before, where NFM is the list of all of the occupation numbers of each possible single particle fermion state, and NBM is similarly the list of all the occupation numbers of each possible boson mode. Now, these states will be the eigenstates of the unperturbed Hamiltonian, which we will take in the form we've been looking at here, analogous to the zero-order perturbation theory equation that we remember from before, where these are the energy eigenvalues associated with these energy eigenstates of the unperturbed Hamiltonian. We will now write this in this form here, where we're using this notation to discuss the eigenstates of the unperturbed system. That is, before we turn on the interactions between our fermions and our bosons here. So Em would be the energy of this fermion-boson system in state M, in the absence of any interaction between the fermions and bosons. Note, incidentally, a key point here. Previously, we might have considered this just to be the wave function of the electron. But now we're saying this here is the eigenstate of the entire, but uncoupled, system. So it includes not only electron energies, but also boson energies in modes here. Now, the actual system state is going to be some linear superposition that we can still choose to write as psi if we want, where we expand this state in our multiple fermion and multiple boson occupation number basis. That is, analogous to the previous kind of expansion we wrote down when we first looked at time-dependent perturbation theory, here we can write an exactly analogous expansion. We're not really changing anything here, except we're now being slightly more careful about what we mean by the unperturbed states of the system. Remember, these now also include the unperturbed state of the electromagnetic field expressed quantum mechanically. And just in a minor change of notation, we're using C here where previously we used A before, so we don't get confused with annihilation and creation operators for particles. So otherwise, this is really the same as we had up here, but with a slightly more sophisticated view of what the eigenstates are over which we're expanding, and some minor changes in notation. We're going to use M now instead of N, and we're going to use C instead of A. Again, we've explicitly included the time factors in here, just as we did before, so we can leave them out of our formal statement of the states. Note again that in an expression such as this that we've just written down as some linear superposition of all of the possible unperturbed energy eigenstates, in contrast to previous approaches, as I said, which treated perturbations as external phenomena, Em is the energy of the complete unperturbed fermion-boson system in this state, and it's not merely the energy of the fermion. We now proceed exactly as before to set up time-dependent perturbation theory. We're really not changing the nature of the time-dependent perturbation theory, we're just making a minor change in notation, and more importantly, we're adding in the boson field as well into our discussion of the eigenstates. So the only real differences are that the basis states are the states of the entire system, and the unperturbed eigenvalues, Em, are those of the entire unperturbed system, which here is one of fermions and bosons. So, as before, with our linear superposition here, an arbitrary state at the moment, and this Schrödinger equation now with a perturbing Hamiltonian, just as before, now the full time-dependent Schrödinger equation, we can eliminate terms on both sides using this relation between the effect of the operator on the eigenstate and the energy of that eigenstate times the state on the right. And we pre-multiply by some specific state Q, that is a list Q of occupation numbers of both fermions and bosons. And we obtain, completely analogously to previous results, this kind of equation. So this is exactly the same kind of equation as we had before, but with our minor changes in notation really here. So we pre-multiplied on both sides of an equation like this one here with this example state, and we're writing out the wave function as we had before, or now more fully the actual complete state of the system using this occupation number notation. So, taking the usual perturbation approach of basing the first order change in wave functions on the zeroth order state, that is, on the unperturbed wave functions, we have now, analogously to the equation we would have before, this equation that we've just written down. And in this equation here, as before, we typically presume the system, here an electron-photon one, starts in some specific basis state, which we could call S here, of the unperturbed problem, so that this starting coefficient is 1 and all the others are 0. We don't have to make that assumption, but we're usually interested in what happens when we start in some specific state, and it keeps our algebra simpler here also if we look at that case. So we have this expression now instead of this more complicated one with the sum. We just said only this coefficient is 1 and all the others are 0, so the sum becomes very simple, leaving just one term. This is the same as we did before.